Cast is now starting.
All right, let's get started. Hi, everyone, and welcome to our second advanced session on the theory and behavior of inclined screws. My name is Caitlin Cross, and I will be the moderator for today's session. I'm part of the sales and marketing team here at MightyCon, and I'm very excited to be hosting today's webinar. My colleague Keith Porter will be the presenter today. Keith is an engineering graduate and part of our technical support team in our Vancouver office. He is heavily involved in the many research projects we have ongoing with universities throughout US and Canada. Today's session is the result of some of this research. Before we begin, I'd like to let you know that we will be recording today's session and we'll send you a link to the recording on Monday. I'd also like to draw your attention to the panel on the right-hand side. In this panel, you will find a handout section with a copy of today's slides available, and you'll also find a question section where you can use throughout the presentation to ask questions. I just want to note that we will wait until the end of the presentation to actually answer the questions, but you are free to submit your questions throughout the presentation. So without any further ado, I'd like to kick things off by welcoming Keith Porter, our engineer in our technical support group responsible for research. Keith, over to you.
Okay, thank you very much, Caitlin, and thank you everyone for joining this webinar today. So the topic today is the advanced theory and behavior of inclined screws. Once again, my name is Keith Porter, and I'm part of the technical support team here at MightyCon Timber Connectors. So this webinar is intended to be a follow-up to the basic theory and behavior of inclined screws. In the basic webinar, we looked at the simplified truss design model, which considered only the axial effects of the fastener. Today, we're going to look at other design models that consider dowel effects as well. The focus for this advanced webinar has a lot to do with the relative proportion of dowel effects and axial effects, as they both contribute to the total connection strength for inclined screws. So this webinar is going to start off first with a little background theory, and then we'll go into examining the three design models which I have listed over here, and those are the simplified truss model, the combined loading equation, and the Johansson yield theory. So to begin with some theory, in the basic webinar, we looked quickly at the following design example where 8-inch thick timber members were connected with either 1/2 inch diameter laterally loaded screws or 1/2 inch diameter inclined screws. I'm going to begin by explaining how I designed this example to maximize the advantage of inclined screws over laterally loaded screws. For a laterally loaded fastener, when we have a low slenderness ratio, meaning we have a thin timber member and a stocky large diameter fastener, theoretical connection strength increases linearly with increasing penetration depth, as you can see by this red line here. However, as we increase the penetration depth, at some point the connection strength is characterized by the formation of 1 or 2 plastic hinges in the fastener, and this interrupts this linear increase in strength. For the lateral connection design for self-tapping screws calculated according to NDS, once we hit a penetration depth corresponding to a slenderness ratio of approximately 7, our theoretical connection strength is maxed out. The reason why it maxes out can be explained by referencing the photo on the right. Basically, at a penetration depth of 7D, the dowel bearing resistance of the wood within this range here is sufficient to produce a plastic hinge in the fastener. So once this plastic hinge is formed in the fastener, then any further dowel bearing resistance from further fastener penetration length beyond 7D is considered irrelevant. So basically, in theory, at 7D penetration, the lateral design strength is limited by the bending resistance of the fastener. The upper limit for connection strength for inclined self-tapping screws, on the other hand, is not limited by bending resistance, but by the tensile strength of the screws. So as designers, we can ask, at what penetration depth does the failure mode for axially loaded screws change from withdrawal to tensile failure? MightyCon has done extensive testing on self-tapping screws with various wood species and angles to the grain, and as part of this testing, we have kept track of the failure modes relative to the thread penetration depth. The bar chart on the left shows the failure modes for screws in spruce pine fir, and the one on the right for Douglas fir. For spruce pine fir, we start to see tensile failure modes, which are indicated in black, beginning at a penetration depth of approximately 16D. For Douglas fir, which is a denser wood, we see some tensile failure beginning at 8D, but when we get to 16D, we see that it really dominates the failure mode. So based on test data like this, and with further calculation, we can say that we will see connection strength characterized by tensile failure at 20D in spruce pine fir, which is measured along the axis as shown for an inclined screw connection. For screws inclined 45 degrees, this equates to approximately 15D measured normal to the plane. And so for a 1/2-inch diameter screw, our connection strength is maxed out with a timber thickness of approximately 7.5 to 8 inches, which is why it shows this timber geometry for the initial design example. Connection strength for laterally loaded fasteners, however, can still be increased by increasing the bending resistance of the fastener, and one way to increase the bending resistance is by increasing the size of the diameter. For illustrative purposes, if we used a bolt with a bending yield strength of 45,000 psi, we would need a diameter of 1 1/8 of an inch to achieve a reference lateral design value of 3,000 pounds, which is what we achieved with a 1/2-inch inclined self-tapping screw. Bolts, of course, will always be a part of timber engineering, but compared to inclined screws, when we use bolts, we will also have to consider things like pre-drilling, controlling fabrication tolerances, increased assembly time, and further reductions in the cross-sectional area of the timber. So this makes bolts less feasible for high-capacity connections, especially in mass timber design, where through penetration is always not viable. So this concludes the theoretical section of the webinar, but this idea that the bending resistance limits lateral connection strength at certain penetration depths will be referenced as we move forward. At this point, we're ready to have a closer look at a few design models for inclined screws. So first off, I'd like to provide a quick overview of the 3 models before going into them in more detail. In the basic webinar, we looked at the simplified truss model, which is shown here. The simplified truss model is based on the idea that at certain angles, axial effects predominantly characterize connection strength and behavior. Consequently, the design model considers only axial effects as the design parameters. On this slide, I'm including the basic equation for a single inclined screw for both US and Canada. As you can see, the axial resistance is the minimum of the withdrawal resistance or the tensile strength of the screw. For our lateral resistance, we take the cosine component of this axial force, and we also include friction in our design model. The next design model is the combined loading equation. This equation is a second-order interpolation equation, and it is included in the NDS to give an adjusted design value for loading at angles between purely axial loading and purely lateral loading. This equation is intended for loading scenarios like the one shown here, where the fastener is loaded away from the surface of the wood. Nonetheless, we can still assess its suitability for inclined screw connections. And the final model we'll look at is the extended Johansson theory. Because this model was derived specifically for inclined fully threaded self-tapping screw connections, and because it's the most comprehensive model we have, we can compare it to the truss model to see just how much the axial effects contribute to the total connection strength. So we'll start with the simplified truss model and then go right into a design example. So first off, looking at the specimen where we have 8D thread penetration in the side member. Using American allowable stress design values and setting the contribution of friction to 0 on the account of the fact that we use Teflon in our testing, we get a short-term lateral design value of 4,800 pounds for 8 screws, where the failure mode is characterized by the withdrawal of the screws in the side member. On this chart, we can see how the design values compare to the ultimate value achieved in testing. So I've also included the Canadian factored resistance as well for reference. For the American design values, here we achieve a factor of safety of approximately 5.9. So interestingly, we can remove the factors of safety from the withdrawal values, and by doing this, we can estimate the peak connection strength by assuming all connection resistance is a result of axial effects, just as we do in the truss model. When we do this, our prediction is 16,700 pounds, which comes short of the peak resistance of 28,200 pounds. So the tested peak resistance is still 1.7 times greater than what is estimated, so we're estimating at approximately 60%. So at first, it would seem as though the simplified truss model is leaving a lot of connection strength on the table, so to speak. However, we will see that this is not always the case, and we'll see that when we look at this next specimen. So here we're looking at one where the thread penetration depth is 20D in the side member. And using American allowable stress design values, and once again setting the contribution of friction to 0, we get a short-term lateral design value of 9,000 pounds for 8 screws, and this is where the failure mode is characterized by the tensile failure of the screws in the shear plane. Once again, I've plotted both the Canadian and American design values over the load displacement chart for this specimen for reference. For the American design value, here we achieve a factor of safety of 4.0. And as before, we can attempt to predict the peak connection resistance by removing the factors of safety from the allowable tensile strength of the screws. This time we have a peak resistance that's only 1.2 times greater than what we predict. So interestingly, when we tested a variety of configurations with inclined screws, this pattern seems to come up again and again. And that is that the Truss model seemed to predict peak resistances most accurately when high thread penetration lengths were employed in the design. I'll explain how I understand the reason for this as we move on. Next, we'll look at the combined loading equation, which is found in the NDS. This equation is set up to give an interpolated design value for loading at angles between purely axial and purely lateral loading. Mighty Kant also publishes this formula in our structural screw design guides. As you can see, the formula uses the axial resistance and the lateral resistance as parameters, with the angle theta referenced against purely lateral loading. As I mentioned before, this equation is primarily intended for the loading scenario shown here, where the threaded fastener is loaded at a direction away from the wood surface, as shown here by Z prime theta. But nonetheless, we can still adapt these parameters for the inclined screw model as such, shown here. So as before, I've kept theta defined by referencing it to purely lateral loading, which is perpendicular to the axis. Since we're modeling dowel effects perpendicular to the axis, the dowel bearing resistance is modeled as shown here. And this means that for large diameter fasteners, we would also need to work out the dowel bearing resistance at an angle between 0 and 90 degrees to the grain by using a Hankinson expression for bearing resistance. In fact, you'll also notice that the combined loading formula is in the same format as the Hankinson expression as well. So on to the design examples. In the case of the first specimen, where we have 8D thread penetration in the side member, we have a short-term adjusted axial capacity of 940 pounds per screw and an adjusted short-term lateral capacity of 400 pounds per screw. This means that the ratio of the axial capacity and the lateral capacity is 2.4, and I'll explain the reason for mentioning this later. With 8 screws, we have an adjusted combined loading value of 4,600 pounds compared to a value of 4,800 pounds when calculated according to the cosine component idea of the Truss model. So here it would seem that when we disregard the effects of friction, at least in our Truss model, that there is reasonable agreement between the two models. However, when we look at the next specimen, we'll see that this is not always the case. For this specimen, where we have 20D thread penetration in the side member, we have an allowable tensile strength of 1,775 pounds per screw. And for the short-term adjusted lateral design value, we have 400 pounds per screw. So you notice that this is the same as it was with the previous specimen, and this makes sense because we remember that lateral connection strength is maxed out theoretically at 7D penetration. Our ratio between the axial and lateral capacities is now 4.4. The combined loading gives us an adjusted combined loading value of 5,400 pounds with 8 screws. And when we compare this to the Truss model, we have 9,000 pounds. So now we see that there's a big difference between the two models. And this indicates that the combined loading equation is probably coming up short. So the reason for this discrepancy is, I think, made clear when we look at the format of the combined loading equation here. Basically, if the ratio between the axial capacity and the lateral capacity is relatively small, then the combined loading expression will give us a nice interpolation between the two values. However, for long, fully threaded self-tapping screws, it's easy to achieve high axial capacities. So basically, as we move away from purely axial loading, as shown here, the axial capacity, if it's very large relative to shear capacity, then the denominator down here will grow very rapidly as we move away from purely axial loading. And when the denominator grows rapidly, the whole connection strength is dragged down with it. This effect is clearly seen here on this chart for American design values. The upper bold line shown here represents the cosine component of purely axial loading, which is basically the approach that we take using the Truss model. The lower dashed lines here and here show how rapidly the combined loading equation drops off as we move away from pure axial loading. So for an axial to lateral capacity ratio of 4.4, we are reduced to less than 40% of the full axial capacity at 45 degrees, while the cosine component still gives us 70%. If we apply the same formula to Canadian design values, we can see that the trend is even worse for the two specimens. So for the lower dashed line, the axial to lateral capacity is 14.7, and here the combined loading value is reduced to 10% of the full axial capacity at 45 degrees, compared to approximately 70% when we take the cosine component. It's also worth mentioning that in Eurocode 5, which is the European Timber Building Code, there's a second order interaction expression for the combined loading scenarios. It's generally found to produce results that are similar to the formula that we went over in the NDS. So this was also assessed in terms of its suitability for inclined self-tapping screws in the study that's cited over here. According to this study, the interaction equation was also found to be safe, but also overly conservative, as you can see in this chart. We have tested values on the above line here, and on the lower line, we have the interaction formula. So you'll also see, looking at this chart, that there was much better agreement between test results and theory whenever we use the extended Johansson theory, and that's the final design model that we're going to turn to now. The extended Johansson theory was derived specifically for fully threaded self-tapping screw connections. So when it comes to inclined screws, the extended Johansson theory is the most comprehensive model that has been developed so far. As you can see, it not only includes the axial effects and friction, like the Truss model does, but it also includes dowel effects, such as the bearing resistance and the bending resistance as well. The idea with this model is that we're combining the lateral resistance of the screw, which shows plastic capacity, with the axial capacity of the screw, which does not really show much capacity for plastic behavior. Since we're not modeling stiffness compatibility in our design model, when referencing the ultimate limit state, we need to be assured that the lateral design capacity is reached before the ultimate axial capacity of the screw. So as a consequence of this, we should not assume that the model will work with very low angles. So far, the extended Johansson theory has been assessed primarily for angles between 45 degrees and 90 degrees to the shear plane. It's important to note that while the Truss model has been proven to work very well for angles as low as 30 degrees, we should not assume that the full design strength for lateral loading can be developed at very low angles, because basically we might get the relative axial and dowel behavior like the kind illustrated here. It's also worth mentioning that for high angles above 60 degrees, it's sometimes proposed that the full axial capacity cannot be assumed for when the connection reaches its ultimate load. So to account for this, a reduced withdrawal parameter is sometimes used instead, which is approximately 70% of the full axial capacity. This is something that I think should be clarified through further research. In the open specimen here, which uses an angle of 75 degrees, here we have physical evidence that both the full lateral resistance and axial resistance was developed. So here you can see crushing of the wood around the shear plane, bending in the fastener with two plastic hinges indicating a type 4 failure. And we also see evidence of withdrawal failure since the screw is being pulled into the wood in the side member. The derivation of the extended Johansson theory is based on the undeformed state of an inclined fastener as reproduced here. As you can see at the shear plane, there's an accounting for the axial force normal to the cross-section of the screw. There's the normal force at the shear plane, the friction force. We have the shear force perpendicular to the screw axis. We also have the dowel bearing strength as modeled perpendicular to the axis, just as I've been doing in this presentation up until now. And this parameter F1 that you see here and here is the withdrawal resistance, which I've mentioned is sometimes modified for high installation angles. So just as with the standard European yields model or the yield limit equations, here we have 6 possible failure modes that we need to consider. So presented with the set of design equations, they can look very cumbersome to most designers, and this is the reason why most designers prefer to use the Truss model design method, even in Europe. However, we don't have to go through every one of these failure modes if we remember what we covered at the beginning, which is that at certain penetration depths, our lateral connection resistance will be characterized by failure mode 4, which I've indicated here. So reproducing this expression for failure mode 4 and rewriting it to conform to how I have been defining the angles rather, we have this expression here. Furthermore, if we have the same wood properties for both members, then this part of the equation can be set to unity. So basically, we have taken a very large set of equations and turned it into something that's pretty manageable, and we're going to be looking at this expression for the rest of this webinar. It's also worth noting that this is similar to the approach taken in the study that's cited at the bottom here. So the first thing you'll notice is that the first term in this equation is basically the Truss model equation. So this term here, indicated in the box, can basically be thought of as the term that's modeling axial effects alone. The second term represents the additional strength from the lateral component. So this is the component that's not considered by the Truss model, and here we're going to be calling it the Johansson component. I'd like to stress that so far the extended Johansson theory has only been assessed using European design parameters. So for the last analysis, I'm using European design parameters and design values as well. So what I'm really interested in with this analysis is how much theoretical connection strength comes from axial effects alone. Computing through this expression and changing only the penetration depth in this column from 8D, which is low, to 20D, which is high, we can see the same pattern as we did previously by looking over here. At low thread penetration depths, where the ratio between the axial capacity and the lateral capacity is less severe, the proportion of the connection strength being neglected tends to be higher, in this case, 27%. However, for longer thread penetration lengths, such as 20D and spruce pine fir, by assuming axial effects alone, as we do in the Truss model, it looks like we still achieve approximately 85 to 90% of the total theoretical connection strength at an angle of 45 degrees. So we're going to wrap things up. Since we've covered a lot of ground, I'll sum everything up on the final slide here. In the basic and advanced webinars, we focused a lot on the Truss model design method because this is the easiest to adapt to North American codes, and also because it's the most widely used approach in Europe. For design in North America, all you need is code-approved withdrawal and tensile resistances for your screws. Since the Truss model considers only axial effects, we found that it tends to be increasingly accurate for low installation angles and also for long thread penetration lengths. We also looked at the second-order combined loading equation and found it to be safe, but also too conservative for connections with fully threaded inclined screws. Finally, we looked at the extended Johansson theory. I gave some hints as to how I think this model can be simplified for practical design purposes. But until this model is assessed using North American design parameters, it should not be considered for use in North America. Still, this model seems to confirm what I said earlier about the accuracy of the Truss model, which is that when we are designing high-capacity connections, the Truss model tends to give very good agreement with reality. So one other thing I'd like to mention is that for designers interested in designing with inclined screw connections, we are currently working on our design procedures being included in the next revision for ICC product approvals, which we hope to have completed sometime soon. For North American design values, you'll find these in our product approval reports, or you can also look in our structural screw design guide, which is available online. And for designers in the US, we've recently released a connections guide for CLT. A lot of the concepts that I've talked about in this webinar are included in this handbook. For anyone watching this webinar today, you'll get a 15% discount code, which will be sent out in the follow-up email. So this concludes the Advanced Theory and Behavior of Inclined Screws webinar. I'd like to thank you all very much for participating today. And at this time, I'm going to hang out online. I'll see if there's some questions that have come in that I can answer within the next few minutes. For any questions that I don't have time to get to today, I'll do my best to answer those in the follow-up email. Okay, the first question here is, in the simplified truss model, where does the normal force come from? Clamping, and why is it pointing downwards? The figure the speaker shows does not show equilibrium with the direction of the forces. Basically, when you have a connection, you can think of the centroid of the force as going through the like the center of the member. So you always have this, eccentricity or eccentricity. Because of that, then the connections want to be flattened out and pressed against one another. The incline screw connection, it does not provide any clamping force, at least with wood-to-wood connections. There is some clamping force with steel-to-wood connections because threads don't engage with the steel plate. But this normal force is basically the result of eccentricity in the connections and slight deformation of the fastener and the wood. I'll also mention with that idea of including friction, we're basically assuming that these joints are going to be assembled properly. Sometimes it's mentioned that maximum gap width for an incline screw connection should be limited to 0.2 times the diameter. So basically the wood should be, you know, a nice tight seal. The fully threaded connection shouldn't be holding any gaps between the members. And with that, you can assume that the normal force will be activated as soon as the connection is loaded. And because there's a normal force that's activated, then you include friction in the design model. The next one is, how do you determine the factors of safety? This is determined according to standards in the American approach to new fasteners. The standard approach for screws and withdrawal is to have a factor of safety of 5.0. And for the tensile strength of the screws, we have an allowable tensile strength based on a factor of safety of 3.0. This next one is about the extended Johansson theory. Is the extended Johansson theory available to North American design standards, or is it only applicable for use with EC5? And I did touch on this. I think I talked about this in the webinar, but I'd like to explain why I believe it shouldn't be used yet. Some of the parameters are a little bit different. Some of the assumptions made in the yield models are a little bit different between the codes. And so you shouldn't assume that the embedment strength in one code is directly interchangeable with another one. I think that converting between European and Canadian codes is a little more straightforward than converting between European and American building codes. Nonetheless, anyone that wants to study this, I think they should take a good look at what are the assumptions in the yield model, how they arrive at these design parameters, and really make sure that the parameters that they include are carefully examined before they use them in the model. Next one is just to clarify, CSA 086 does not provide an interaction style equation for combined lateral and axial loading. Does MightyCon recommend using the simplified truss model and using the screw's axial capacity only? Yes, as far as I know, CSA 086 does not provide an interaction style equation for combined lateral and axial loading. The one that I mentioned is only found in the NDS. It is based on a study with lag screws that had a thread penetration, or sorry, a thread length of approximately 4 inches. And does MightyCon recommend using the simplified truss model? Yes, this is totally what we recommend. It's proven to be safe. It's very easy to use. And because we have tested values for our axial capacities for self-tapping screws in North America, it's something that we can be applying right away. So there's a few more questions here, and I think there's going to be some really good ones that are coming in too. I'm going to let the webinar run, so if you have a question and you haven't submitted it yet, please submit it now. At this point, I'll wrap things up, and I'll turn it over to Caitlin just to close things off for the day.
Perfect. Thank you, Keith. And thank you, everyone, again, so much for joining us today. As a reminder, we did mention that we will be sending a follow-up email on Monday, and that will include all these questions and answers. We'll type them up and send them to you so everyone has access to them, the PDF slides, as well as the video recording. And if you do have any further questions, if something comes to mind later on, you're more than welcome to reply to that email or just reach out to us at the email on our website, which is info@mightycon.com. And once again, as Keith mentioned, you have another 10 minutes or so if you want to continue to write questions on here. We will answer those and include them in that PDF we send on Monday. I hope everyone enjoys the rest of their day, and thank you again so much. Have a nice day.